Okay, so hopefully some of you had this thought after going through the last video, which is, what if we have more than two decisions to make? It's very rare in life that you are faced with any sort of situation, and it's limited to only really at the very fundamental basis having to make two decisions to answer whatever to address whatever situation you're working with. And, even in the outfit example, only having to choose pants and a shirt, well, you wouldn't have socks on, you wouldn't have underwear, you wouldn't have an undershirt, you wouldn't have shoes on, right? So or a hat, right? Whatever the situation might merit, or a coat if it's cold, or a scarf, right? So there are a lot more than two decisions that go into any one of these situations in real life. So, what do you do if you have more than two decisions to make? All right, so let's again look at an example. Let's again look at the number of outfits. All right, so how many outfits are possible? From, let's not make it too complicated. Let's say maybe two pairs of pants, two shirts, and let's say two pairs of shoes. All right, so what we're going to do is just go ahead and list these out the same way we did before. All right, so we're going to label the pants P1, P2, shirts S1, S2, shoes we run into a little bit of a problem because we're already using S for shirts. So maybe let's call them H1 and H2. All right, our shoes are going to be labeled H1 and H2. And what we want to do here is just go ahead and start listing them out, right? So if we've got pants 1 first, well, to pants 1, we could match shirt 1, or we could match shirt 2. Now, to shirt 1, we could match shoes 1, or we could match shoes 2. To shirt 2, we could match shoes 1, or shoes 2. All right, so if you're counting the total number of options that this gives us, well, this gives us what looks like, that would be one outfit right there. That would be another outfit with H2 instead of H1, so that would be two outfits. Down here would be three outfits, or pairing up H1 instead would be a fourth outfit. Right, so each one of these gives us 4 outfits. All right, and you could do the exact same thing for pants 2 instead of pants 1. Right, so pants 2, and it's going to look identical to the diagram I just made. All right, so pants 2, you can match up with shirt 1, or you can match up with shirt 2. You can match these up with H1 or H2. You can match this up with H1 or H2. And so this again gives you 4 more outfits. All right, so the total number together, right, so the total number of outfits is 4 plus 4, which is 8 outfits. From the options you have available to you, which is 2 pairs of pants, 2 shirts, 2 pairs of shoes. That gives you 8 total options. Right, and again, being the pattern recognizers that we are, we have two options for decision 1, being the 2 pairs of pants, two options for decision 2, being the 2 pairs of shoes, the 2 shirts, and two options for decision 3, which is the pairs of shoes. Multiplying those together, 2 times 2 times 2, gives us the 8 total options that we found by drawing them out using diagrams and taking up a lot of time and space. Right, in other words, the same fundamental counting principle still applies. We still just multiply together the total numbers of things that we have, and multiplying them all together gives us the total number of options. All right? So one way that you could view this, right? One way that you could sort of realize this on your own is by sort of breaking it down systematically and saying, okay, if I need to make these 3 decisions together, I forgot why I scrolled up. If we need to make these 3 decisions together, right? Pants, shirts, and then shoes. Well, we could instead view this as making pairs of decisions on a smaller scale, right? So if I need to first choose pants, then shoes, then shirt, then shoes, I could instead look at it like I'm going to pick pants, then shirt, and then from each one of those decisions, I'm then going to pick a pair of shoes after that. All right, so let's view it that way. If we do pants and shirt first, well, the fundamental counting principle says that we're going to have 2 times 2, which is 4 total ways of combining the pants and the shirts. All right, and I can use the fundamental counting principle because I only have 2 decisions to make. And the fundamental counting principle very explicitly applies to pairs of decisions. Just, one thing combined with one other thing. And so I can say, okay, I've got 2 pairs of pants, I've got 2 shirts, I can multiply those together using the fundamental counting principle to tell me that I have 4 ways of making pants and shirts together. Now, what I'm going to do is I'm just going to be a little bit annoying. I'm going to say that decision 1, right, so before decision 1 was pants and decision 2 was shirt. Now I'm going to say decision 1 is the choosing of the pants and the shirt together. And decision 2 will be choosing the only thing left, which is shoes. Now, what we just saw is that we had 4 ways of choosing pants and shirts together. Right? There are 4 ways of doing this. And the shoes, well, we know that we only have 2 pairs of shoes, so there are 2 ways of choosing the shoes. So now I've got a decision, which is pants and shirts together. There's 4 ways of doing that. And I've got decision 2, which is the shoes. There's 2 more ways of doing that. So now the fundamental counting principle can be applied to this situation. The total number of ways of doing this is going to be 4 times 2, which we already saw is the correct number of ways of doing this, which is 8. All right, so this is 8 total outfits. All right, so our fundamental counting principle can be sort of adapted to work when you've got more than just 2 decisions that are going on. In math, this is a technique that we often call bootstrapping, right? So we're bootstrapping this fundamental counting principle up to a more complicated scenario, which has a lot more decisions possibly, and yet we can still break it down into pairs of decisions and have what we already know how to use apply to that new scenario. All right, so this can lead us to something which we can call the generalized fundamental counting principle, which is stated on the next page. So the generalized fundamental counting principle just, it does exactly what we want it to do. It's going to take our fundamental counting principle, which only applies to pairs of decisions, so just decision 1 and decision 2. And it instead, it soups it up to now deal with possibly a lot of decisions, K decisions, right? So k could be 2, k could be 3, k could be 40, k could be 170 million, right? K is just any positive integer. And if we have to make k decisions, and we've got a certain number of options for each, so we're going to give the number of options for each decision that we can make a different name. All right, so let's say we have n sub 1 options for decision 1. Right, so maybe we have like 6 options for decision 1. N sub 2 options for decision 2. So maybe we have like 3 options for decision 2. And in general, we're going to have a different number of options for each one of these decisions that have to be made. And we'll call the last one n sub k. That's the number of options we have for decision k, which is the last decision we have to make. All right, so a possibly different number of options for each one of these many decisions we have to make. Then the total number of ways of making all these decisions together is found just by multiplying them together, like we did when there were only 2 decisions to make. Right, we multiply n1 times n2 times n3 times n4 all the way down the line, eventually multiplying with the last number of decisions we have, which is n. The last number of options we have for the last decision, which is n sub k. Alright, so we just multiply all these things together, and that gives us the right number of decisions. Or rather, the right number of ways of making the decisions, I should say. Alright, so we can very quickly do an example. Call it example 2. If we have, we want to figure out the number of outfits from, let's say, 3 pairs of pants, 6 shirts, 2 shoes, pairs of shoes, that is, of course, and let's say 5 pairs of socks. Right, of course, that's pairs of socks, not individual socks. How many outfits can we make from all of these things? All right, so our generalized fundamental counting principle says that the total number of outfits will be just multiply all of these things together. 3 pants times 6 shirts times 2 shoes times 5 socks. All right, so let's see here. 2 and 5 together make 10. 3 and 6 together make 18. Multiplied together, this is 180 total outfits. All right, so that's a lot of outfits. And this is a very quick way of using the the generalized fundamental counting principle to answer a question like this, which seems like it should be a relatively straightforward question. It would be very, very complicated to write out all the diagrams for this. But using the generalized fundamental counting principle, it's actually fairly straightforward to calculate the total number. So let's consider something a little bit different. At least it's going to look a little bit different. All right, so for this third example, let's make the problem look a little bit different. Let's say how many ways can we order maybe 7 books on a shelf? All right, so when I say order, I just mean, put them on the shelf in some specific order. Okay, so, we have 7 books here. So B1, B2, B3, B4, B5, B6, B7. And so what I've just written down here is one way that we could order all of these 7 books on the shelf, right? Whatever book 1 is, we could put first. Whatever book 2 is, we could put second, and so on and so forth. And this is going to be a distinctly different ordering. Right? This is going to be a different ordering than if we put book 2 first, and then book 1, and kept all the others the same. Right? And this is still going to be different from if we did, book 2, then book 1, then book 3, then book 5, then book 7, then book 4, then book 6, right? These are all different orderings of the books on the shelf. So the question is, how many different ways can this be done? So, what we need to do is think about this problem in the context of the fundamental counting principle. That is, think about it in the context of different decisions that need to be made in some sort of order. So, one way we can think about this is, right, if you just want to think about any old ordering of books on the shelf, let's say that that's spot 1, and that's spot 2, and 3, and 4, and 5, 6, and 7 on the shelf. Right, so we have 7 open spaces on the shelf. Well, let's think about how many different options we have, right? How many different ways could we decide which book goes first? Well, we have 7 books available to us, and so the total number of things that could go first on the shelf would be any one of the 7 books. Right now, deciding what's going to go second on the shelf, we only have 6 books left, because we've already decided that one of them, right, a very specific book, should go first. So we remove that book from consideration, because it's already on the shelf. That leaves us with 6 left that can go in spot 2. Now we've chosen 2 of the books on the shelf. That leaves us with 5 that could go third, 4 that can go fourth, 3 that can go fifth, 2 that can go sixth, and 1 that can go last, 7th. And our generalized fundamental counting principle says that we should multiply all of these ways of making these decisions together to figure out the total number of ways that we could order the books on the shelf. All right, so what this says is that by the generalized fundamental counting principle, the number of orderings is going to equal 7 times 6 times 5 times 4 times 3 times 2 times 1. And remember, this is what we called 7 factorial, denoted by this exclamation mark. And if you're really curious, you really like knowing what numbers are that aren't, weird exclamation mark numbers, this is 5,040. That's a lot. Okay, so let's change this question a little bit. All right, so let's call this example 4. What happens if we have 7 books available to us, but maybe we only want 4 of them on display? All right, so let's say, how many ways can we order 4 books on the shelf from the 7 that are available to us? Okay? So I want you to take a minute, think about how you would approach this question. Right? Try to take the same approach that we took in the last example, and take at least a few minutes on this if you need to, right? Set aside 5 minutes and work on this. Pause the video and see if you can answer this question using the generalized fundamental counting principle. All right, so pause the video right now, go work on that, and then come back when you are either so stuck that you are about to walk away, or if you come up with an answer. All right, so now that you have either become hopelessly stuck or you have come up with an answer, let's go ahead and see how this should work. All right, so again, the fundamental idea is the same. We've got a book that should go first, we've got a book that should go second, a book that should go third, and a book that should go fourth. And now for each one of these positions on the shelf, we just need to say how many ways we have of deciding which book goes in each spot. So we have 7 total books available to us that could go first. We have 6 books left after we choose the first one. After we choose the first 2, we have 5 books remaining. And after we choose the first 3, we have 4 books left that could go fourth on the shelf. The generalized fundamental counting principle tells us to multiply all these things together. All right, so this says that we should have 7 times 6 times 5 times 4 total options. Now this number is not nearly as nice to go ahead and directly calculate, in particular because, for instance, Google can tell you what 7 factorial is. You just type in 7 factorial, and it will tell you what the value is. This one you would actually have to type in 7 times 6 times 5 times 4. So let's just go ahead and do it here by hand. 5 times 4 is 20. 7 times 6 is 42. So we've got 42 times 20. So let's see here. 42 times 2 would be 84, and throw 0 on the end. So that's 840 different orderings. Still a lot of orderings of the books. All right, and again, it came down to the fundamental counting principle, just interpreting the question in a way that can allow you to use the fundamental counting principle to answer it for you. All right? So what we're going to do next is basically the same idea, except we're going to suppose that order no longer matters. All right, so in the next video, we're going to tackle the question of, for instance, how many ways can we choose 4 books from the 7 that we have, with order not mattering. All right, so we're just going to throw those 4 books into our backpack and go to the library or whatever. So in the next video, we will tackle that question.